Hello, welcome to the wrap up of our discussion on the CPU. Today, we're going to go through the CPU from scratch, sort of. So we're going to start with the building blocks that we've already developed in the class so far, and then see what needs to be done to bridge the gap between the CPU that we're going to build and the components that we have developed so far. So this is the not so basic basics of logic design. Okay, so far we have covered all of the things in purple. We've looked at how to add, we know how to select between a couple of different inputs using a multiplexer and the select lines on that multiplexer. We know how to add again, and we know what's going on in the ALU. What we don't know is what's going on inside the program counter, the instruction memory, the registers, or the data memory. But we know more or less because we've already talked about how a register works. And these are just basically complicated versions of registers. So today we're going to be jumping into these program counter, instruction memory, register file, data memory, and then we're going to put all that together into the CPU. Quick reminder. This is how we showed the register working previously, right? So it has 4 inputs in the case of a 2-bit register. So it's only able to hold a 2-bit number. So bits 0 and 1 are the value that is stored in this 2-bit number. And there may be multiple registers, and so we have to set load to high if we want to store in this particular register. Right? This one that we're depicting on the screen right now, this whole thing is the register. And then it actually stores to the register on the falling clock edge, right? So we set the value, turn on load, and then when the clock edge falls, the value updates. Well, if we move that over into the NAND game, we see something very similar, right? So each one of these is a D flip-flop, and we have these connected to bits 0 and 1. So we have 2 D flip-flops, which we have developed previously, and we've seen how to build those. And we have inputs D0 and D1. And then we have the clock signal that is going into these D flip-flops actually being controlled by both the clock and the load. So this is how we actually build the register in the NAND game. Or one way we can build the register in the NAND game, I should say. So we know that. We've seen that. How do we go from a register to a program counter? First, it's important to realize that the program counter, it really is just a register. It's a register which has a value going out, which is going to point at the instruction that we want to execute. And it has a value coming in, and this is the next value that we want to store in our program counter. So we have a single register. Its output values are mapped to the program counter 0-bit and program counter 1-bit. And then we have these 2 inputs called next 0 and next 1. So this is the next program counter value that we want to come in. And we map those into data 0 and data 1, which are the values that are going to be stored in our register. And then we take our clock input and we map it to the clock input of the register and the load input of the register. The reason is we are going to update our program counter on every cycle of the CPU. So on every cycle of the clock, we are going to update this program counter. So we don't need to worry about a separate load input because there's never going to be a program counter step, a clock step, I should say, sorry. There's never going to be a clock step where we don't update our program counter. So we have our inputs, clock, next 0, and next 1, and we have our outputs, program counter 0-bit and program counter 1-bit. This is going to allow us to address at most 4 instructions, right? So this is a 2-bit number that is being output from our program counter, and the highest, or we can have 4 numbers represented by a 2-bit number, 0, 0, 0, 1, 1, 0, and 1, 1. So we can have 4 instructions that this program counter addresses. So now we're going to talk about the register file. So we've talked about the program counter. We've seen that the program counter really is just a single register. Now we're going to look at what's going on inside this register file. It's a little more complicated than the program counter, but just because we have to scale up. Okay? So first, let's understand what the inputs are. Let's understand what the outputs are. And then we'll deal with what's going on inside this thing, which is a lot of crisscrossing lines. But the inputs, right, we have clock, we have the source register, and so we have two of those, right, because we know in the instructions we've seen, like add, we have add, the destination, source register 1 and source register 2. So it's the same thing here, right? We have the clock input, we have the source register 1, which requires 2 bits. So clock input, source register 1, which requires 2 bits. Source register 2, which requires another 2 bits. A destination register, 2 bits. And then the value that we want to store in that destination. And the largest values that our ALU can output is 2 bits. And all of our registers that we are building are 2 bits. So therefore also the value that we can take in to put into our destination register is 2 bits. The outputs of this register file are going to be the values that are stored in RS1 and the values that are stored in RS2. So thinking about this, right? We have 2 bits that we're going to use to select RS1. And then the value is going to get output here. So what that means is if we have 2 bits that we can use to select one of our registers in this register file to then output into RS1, that means that at most we can have 4 registers. Now, if you remember, in RISC-V, register 0, x0, right, is always 0. If I try to write something to x0, it does not get written. It just gets dumped into the nothingness, the void, right? If we read from x0, the value we always get back is the value 0. So we have the same thing here. Our first register is just the value 0. And so just as in RISC-V, if we write to register 0, so we set our destination address to 0, and we put some value in here that we want to store, it's not going to get stored, right? And if we read from register 0, then the value that we are going to put out is 0. But then we have 3 regular registers that we have access to, right? So we have one special register that's always 0, and then we have 3 normal registers. So then if I want to select this register to output its value into RS1, then I would have to put in the value 1 for the 0 bit and 0 for the next significant bit, right? So notice the least significant bit is on the left, which is a little confusing, but it helps the wiring work out nice. So to output the value from this register into RS1, we would need to put a 1 here and a 0 here. Same deal if we want to output this register into RS2, right? We would put a 1 here and a 0 here, and then this multiplexer and this multiplexer will be used to select this register's values and output them in RS2. So all this is actually doing is giving us the ability to choose between one of these 4 registers to be RS1, one of these 4 registers to be RS2, and to select which one of these we want to store the incoming value in, right? So if I want to store a value in, say, register 3, then I pass a 1, 1 into this decoder, which will turn on the load bit of this register. And so on the next falling edge of the clock, whatever value is in this value input will be stored in this register. So we have these two multiplexers are used to select the value that will be output as RS1, and we have these two multiplexers that are used to select the value that will be output in RS2. And then this is the decoder that is used to select which of the registers will store the output value from our ALU. So this is our destination register selector. And this is where we get the values to actually store in that destination register. Okay, let's see what this looks like. So we have the value 0 being fed in for our destination register, which the decoder uses to select that 0th register. But let's change that. We want to select register 2. So we put 2 in for RD, and our decoder selects it. Now let's set the value 3 as our value and give a falling clock edge. So now we see that the value 3 was stored in register 2. So this is how we would go about storing a value in a register, and this is how the register file allows us to do that. Okay, now let's see how we read a value from a register. Notice RS1 has the value 0, so it is selecting register 0, which is our always 0. And then we see we are outputting 0 as the value for RS1. Makes sense. Now let's change that so that we are selecting register 2, and now the output is the value that is stored in register 2, right? It's the value 3. And we'll see it one more time. We're selecting register 0 by putting in 0, 0 into RS 0 and 1, and this is causing the output value in RS1 to be the value 0, right? Now we change our selection for what we want RS1 to output to be register 2, and so now the value in register 2 is output as RS1. Okay, so we've seen the program counter, we have seen the register file. Now we're going to take a look at data memory. Before we do, data memory is almost identical to, in concept, the registers. The main difference is how they are routed to the ALU. So the ALU is directly wired, and we can see it here in this diagram. So the ALU is directly wired so that the data that is read out of the register, so this is like RS1, right? And this is RS2. The data that is read from these registers can be directly manipulated by the ALU because it's wired directly to that register file. But the data memory is not like that. The data memory is not wired directly to the ALU. And so if we want to manipulate something stored in data memory, we first have to read it into a register, and then we can manipulate it in the ALU. So the data memory is just a bigger but further away storage area that we can use in our overall computer architecture. But now let's see how it works. So I want to make a note here. The processor that we're going to show at the end does not have any data memory. And you can do this if you have a simple program where you don't need much memory, right? The processor, the CPU, can rely exclusively on registers if you don't need long-term storage or a lot of storage. But this is not practical in a real processor, obviously, because our register file only has 3 usable registers because one of the 4 registers isn't always 0. So we only have 3 usable registers. So that's not very much storage. The reason that I did not include data memory in the CPU in the NAND game is because the NAND game has limits on the size of a component, right? You can make the window where you display the components only so large, and then it can't scroll or move, and at some point it just becomes almost unmanageable to continue to wire things. And the data memory requires additional bits in the instruction set architecture for load and store operations. And when you add those bits, that has an impact on the instruction memory size. And then wiring that instruction memory gets really really nasty. It's nasty as it is. We'll see that in a second. But if I were to have included the data memory load and store instruction flags, then it would have been much, much worse. So it is not implemented. However, what we are about to see is an example of how data memory works, implemented in the NAND game, but not implemented in our overall CPU. All right. So up here in the right, we have the data memory implementation, and down here for comparison, we have our register file. So we've got our familiar, always zero register, and then we have our 3 normal registers, and we have our method for selecting which ones we want to output as RS1 and RS2, and we have our method for selecting which one we want to store values into. That's our destination register. Up here, we only have one register output, right? So one 2-bit output. And we still have our 4 registers because we can only address 4 registers if we have 2-bit numbers that our processor can handle, right? So we have 4 registers, and we have our write selection. So we have our decoder that selects which of these we will write, and it does that by setting the load input high to the one that is selected. So right now we have register 0 selected in our data memory, and so the load bit is set to high for register 0. And then we have the value, right? The data value that we wish to store. So right now, if we were to receive a falling clock edge, then we would store the value 0 into register 0. And then if we want a particular register as output, we have these read, right? So RD in this case is not destination register. RD in this case is read, and WD is write data. So read data and write data. So our read data input would allow us to select which of these registers we want to then output. So how is this different from data memory? Or how is data memory different from the register file? Because the register file allows us to output 2 values, right? 2-bit values, while our data memory only allows us to output 1 2-bit value, right? And additionally, we have no always 0 register because we don't need it, right? We're not going to be doing the same sorts of things like using that as using add 0 as a method to load a particular value into a register or something like that. So we don't need that always 0, and instead we have 4 traditional registers. So the data memory really conceptually is not different from the register file. It's actually just a less complicated version of the register file. And that brings us to the instruction memory. The instruction memory is actually the most complicated component of this CPU because the selection logic in the NAND game gets very visually difficult. So the visual programming environment of the NAND game is great, but when you start making instruction memory, wiring it is a challenge. So we'll take a look at it and you'll see what I mean. Okay, so it's a bit of a crisscross nightmare here, but this is the simple version. This is not the full instruction memory. So I want to show this first and sort of let you understand at this level what's going on before we see the real thing. So to understand what the instruction memory is, this is just a collection of registers. So first, let's just kind of step through here, right? So it's a collection of registers that stores instructions. So each of these groups of registers is storing one instruction. And specifically what it's storing is the ALU instruction, right? So this is just the ALU opcode that we've seen before. So this instruction memory just outputs A invert, B negate, op0, and op1, right? So A invert is whether or not you're gonna flip the A bit in the ALU. B negate is whether you're gonna flip the B bit, and set carry in to true. And then op0 and op1 choose between the and, or, add, and set less than instructions, right? So we have 4 groups of registers to store 4 instructions. So it takes 2 registers to store 4 bits because each of these registers is a 2-bit register. So if I want to store A invert, B negate, op0, op1 for our first instruction, it takes 2 registers. And then I have A invert, B negate, op0, op1 for our next instruction, and then so forth, right? So this represents 4 instructions, and specifically it's just the ALU opcode for those 4 instructions. So this is instruction 0, instruction 1, instruction 2, instruction 3. And here's A invert is stored here, B invert, or B negate, op0 and op1. And we are programming these just by directly connecting the data bits to either 1 or 0, right? So this is manually programming each one of these bits to be 1 or 0. Yes, it is not a good way to program, but it's the only way possible in the NAND game. Okay. So in our second instruction, here's A invert, B negate, op0, op1. Just for clarity, just making sure the concept is making sense. But the problem is, right, so the reason this is not our full instruction memory is because we don't just need to store the ALU opcode. We need to, in an instruction, right, let's think about it. If we have an add instruction in RISC-V, we have to designate the opcode that we're going to send to the ALU, but we also have to designate the source address for RS1, the source register address for RS2, and where we're going to store the results. And then there are other things, right? Like if we're actually doing some sort of a jump, because we've seen that. We've seen that if we want to do a branch if equals, it's really just to subtract and you use the 0 flag to decide if you're going to jump or not, right? But you have to have things to tell you to do that. And all those are buried in our instruction, right? All those 32 bits in RISC-V. So we need more memory if we're going to do these additional things like specify all these destination addresses for every one of these instructions. And that's what we have here. Like I said, it becomes a bit of a nightmare. So we have a couple of different groups of things. And let's just go over this first based on inputs and outputs. The inputs are very, very simple. We have a clock input, we have a program counter input, and that's it. So the clock input allows us to change what the output of this is, of this instruction memory is based on our clock. And that's important because that's what we need to do. But our program counter is actually what selects which of these various instructions that are stored in all of these registers, right? The program counter is what selects which of these are going to get output. And it does that by using all of these multiplexers up here. And then again, we're programming this thing by connecting each of the actual instruction binary digits to either 0 or 1 and hard coding them. So let's just see how this is grouped. So first, this is instruction 0, right? This is RS1 and RS2 of instruction 0. This is RD, and if the instruction is an immediate value instruction, so if it should be interpreted as an immediate value, and it being the value in RS2. And then at the end, we have B negate, op0, op1, and if it's a jump. A invert is also part of this instruction as well. So the point here is that if you're going to create instruction memory, right, you have to have enough storage to store your instruction. These instructions for the instruction set architecture I made for this simple CPU, these instructions take up 12 bits. There are 12 bits here. You can count them if you'd like. So we need to store one instruction, 3 groups of 2, because 2 registers store 4 bits, right? Each register is 2, so we need overall 6 registers to store 1 instruction. So this is instruction 0. Here's instruction 1. Here's instruction 2. and here's instruction 3, right? So this is why I said wiring this, there are limits. This is as wide as the NAND game goes, and getting much more here without just losing track of where everything is pretty difficult. All right, so RS1 is stored, the first bit, or the 0th bit of RS1 is stored right here, and we can see that it has the value 0 being stored in RS1's 0 bit. The 1 bit is here. RS2's 0 bit is here. RS2's 1 bit is here. RD0 for instruction 0 is here. The immediate value, and what this does is it says, okay, if this is true, right? If this value is true, it says that the value in RS2 should be interpreted as an immediate value, not as a register selection. Okay. And this is where we store our A invert. This is where we store our B negate, op0, op1, and jump, all just for instruction 0. So when the program counter selects instruction 0, all the gold outline registers are connected to our various outputs, right? And that's what we have right here. We have the program counter is inputting 0. And so if you were to go through here, you could compare. RS1 is exactly what you see here and here. RS2 is exactly what you see here and here, and so forth. Okay, we have now developed a register file, our 2-bit ALU, and we didn't go over that here, but the 2-bit ALU that we have built is the same 2-bit ALU that you would have built in class for the NAND game assignment. We've built the instruction memory. We've built our program counter. There's a few additional things here that I'll point out. So we have this thing called immediate or register, and all this does is select, am I going to use this 2-bit input or this 2-bit input? And that is called a multiplexer. So this is just a special multiplexer that when it receives a 0 in its immediate bit, and this immediate bit comes directly from our instruction memory, which tells this immediate or register if the RS2 value should be interpreted as an immediate, or if RS2 should be interpreted as a value coming from a register. So if immediate is true, it interprets this RS2 selection as an immediate value. If it's a 1, then it selects RS2 here, and that gets selected and put into our processor, our ALU. So this is a multiplexer that selects between the output of the value in a register or the value that is being used to select that register as either an immediate value or the register value. So like right here, we have the value 1 being sent to this multiplexer, and that means that it is interpreting this 0, 1 as an immediate value, and that outputs 0, 1 to the B input of our ALU. The other thing I wanted to point out is this increment or jump logic. And all this does is will increment what is in the program counter unless the jump input is true. If the jump input is true, then it simply copies whatever is in these jump targets to the next, right? And so what this does is that if we have the jump flag set and we have the result of the computation is 0, then we will jump to whatever the jump target is. And the way that happens is it is simply input to the program counter, and on the next clock cycle, our program counter updates to that jump target. So now let's see this CPU in action by writing a program and actually executing something with it. So first, before we do the program, this CPU is not RISC-V compliant. It's consistent with the concepts discussed in the class, but it does not implement the full instruction set architecture. What it does implement is add and or, NAND nor, add immediate, subtract immediate, set less than, and branch equal. And this is going to be enough to write a simple program and demonstrate how it functions. And these are a few design decisions that were made along the way when developing this CPU. First, we have 12-bit instructions. We've already seen that when we discussed our instruction memory, right? So we have the 2 bits for our source register 1, 2 bits for source register 2, 2 bits for our destination register, 1 bit for the immediate, right? This is what tells us if RS2 should be interpreted as a register to be read from the register file, or if the value should be interpreted as an immediate address and directly go into the to the ALU. And then we have 4 bits of ALU control. That's A invert, B negate, op0, and op1, just as we've seen before when we built the ALU. And we have 1 jump bit. And this bit essentially allows us to convert our subtract into a branch if equals, right? So if the jump bit is not set, then when we do a subtract operation, then we are just subtracting 2 numbers. On the other hand, if the jump bit is set and the result is 0, then we are actually doing a branch if equals. And then the other thing to know is that the program counter is actually telling our instruction memory which word it wants it to select. So in RISC-V, our program counter tells the instruction memory which byte to start at, and that's why it counts by 4, right? So every instruction in RISC-V takes up 32 bits, and that's 4 bytes. And so our instruction memory, our program counter, increases by 4 at each step because each instruction takes up 4 bytes. In this CPU, for simplicity, the instructions take up 12 bits, not 32, and the program counter outputs a value that is incremented by 1 for simplicity, right? So the first value of the program counter is 0, the second value is 1, 2, and then 3. And the way to interpret that is that the program counter is selecting the 0th word, then the first word, then the second word, and so on. And in this particular CPU, we would say that the word has 12 bits in it. And so this is just a design decision, as are all of these. And these are not the only design decisions that could give us a 2-bit CPU. Again, as I said, this is not the only way to design a 2-bit processor, but it is one way, and it is the way that I went about designing it. So now let's take a look at the program. First, what this program needs to do is it needs to load the value 1 into register 1. To do that, right, we don't have a instruction that is load. But what we can do is we can use our immediate flag and use that to get the value 0, 1 into the CPU. And we see that right here, right? So our immediate value is stored in RS2. So the most significant bit is 0, the least significant bit is 1. So this is 0, 1. And we have the immediate flag set. So this is saying we are going to use the value 0, 1 not as a register selection, but as an immediate value. Now remember, our goal is to store this value, this 0, 1, into register 1. So that means we need to set the destination address to be 0, 1 also. So we have our destination set to 0, 1. But we do not have that load instruction, as I mentioned. But what we have is a register that is always 0, and we have the ability to add. So what we're going to do is we're going to select register 0 with our RS1 bits, and we're going to set our ALU up to do addition. And so what this is going to do is it's going to add the immediate value 1 to the always 0 register, and then store the results in register 1. That's what this instruction does. So this is our RS1 selection. This is our RS2 selection, which is, remember, least significant bit is on the right, or the most significant bit is on the right. And then we have RD is being selected here. And then we have the immediate flag, which is telling us that the value in RS2 should be understood as an immediate value, right? It's a raw value, not a value that is going to be used to select a register. We have set up our ALU for addition. And then we do not have the jump bit set because we are not going to be doing any sort of a jump here. We're just going to increment our program counter after we are done with this instruction. So let's see this actually play out. So RS1 selects register 0. And so we can see that the value 0 is being fed in to our input A on the ALU, right? That's what we would expect to happen, because our instruction says, hey, register file, give me register 00 as RS1. We know that it register 00 in the register file is always 0, so we see 0 come out as our selection from RS1, and that gets mapped over into our A input, because RS1 always maps into the A input in this CPU. Okay, our immediate or register logic recognizes that the immediate flag is set, and so it knows that it should interpret RS2 as an immediate value, not as a register to select. And so it passes the value through to our B input on our ALU. This means that we are adding, right? Adding because we have op1 set, but not op0, not A invert, and not B negate. So we are adding 0 and 1, and we get the sum is 1. So our ALU outputs the sum of 0 and 1. RD, coming from our instruction memory up to our register file, sets our destination register to 1, and the value comes from the result of our ALU. So on the next falling clock edge, the value 1 will be stored in register 1. Okay, quickly, let's discuss the full program. So we step through in a pretty fine-grained way instruction 0. We're going to go through the rest of the 3 other instructions more quickly. Instructions are going to do at a high level, right? Instruction 0 is going to add the immediate value 1 to the value in register 0, which is always 0, and then store the result in 1. So this just loads the value 1 into register 1. We're going to do the exact same thing here in instruction 1, right? We're going to add the immediate value 1 to the value in register 0, which is 0, and store that in register 2. So this is just storing the value 1 in register 2. So the sum total of these 2 instructions, it puts the value 1 in register 1, the value 1 in register 2. Great. Then we're going to do subtraction, and we're going to subtract the contents of registers 2 and 1 from each other and store it in register 3. So we know what register 2 holds, we know what register 1 holds, they both hold 1. So then when we subtract them, we would expect to get 0, and that's what we're going to store in register 3. Finally, what we're going to do is we're going to add the value in register 2, which by the way is still a 1, with the value in register 3 as 0, and store that in register 0. So the result of this addition, this is a 1, this is a 0, The result will be 1, but we're going to store it in register 0. Remember, register 0 is always going to hold the value 0. So it's just throwing it away, right? Because we don't care about this last instruction as the reality. That's what this sort of shows us. Okay, so let's wait 1 second for this to this GIF to circle back around, and then we will see how this actually plays out. So here we have the program counter is at 1, 1. This is the final instruction. When we increment it one more time, it's going to go back to 0. Okay, so now we're starting from fresh. The first thing we're going to do is store the value 1 into register 1, right? And that's going to happen on the falling clock edge when our program counter increases. Okay, so we just stored the value 1 in register 1 using the immediate values. Now we're going to store the value 1 in register 2, and that's going to happen on the falling clock edge. Okay. So now we have the value 1 stored in both registers 1 and 2, and we are now selecting registers 1 and 2 and subtracting them, and we see the output is 0. Now we have stored that output 0 into register 3, which we're currently selecting, and was outputting the value 0. Now we have restarted because we incremented again, returning us to register 0. Which still has the value, or returning us to program counter 0. And we saw that the register 0 still holds the value 0 because, of course, even though we just stored a 1 in it, no value can actually be written there, and we understand why. So the program we just saw execute, all it did was store the value 1 to register 1, store the value 1 to register 2, subtract them, store the result to register 3, and then add register 3 to register 1 and throw away the result. Now we're going to edit the program. What we're going to do is we're going to change that subtraction in instruction 2, right, our third instruction called instruction 2. We're going to change it from a subtract to be a branch if equals. And to do that, all we have to do is set the jump flag on the instruction. And to do that, I went into the instruction memory and rewired the third instruction's jump flag to 1 rather than to 0. So now, what this does is it's going to store the value 1 in register 1, 1 in register 2, and then if registers 1 and 2 are equal to each other, we are going to jump back to we're going to jump back to instruction 1. To do that, what we're going to do is we're just going to store the value 1 in our program counter. So our program counter starts at 0, it goes to 1, it goes to 2, but then if the values in registers 1 and 2 are equal, our program counter is going to jump back to 1. And then we are going to get stuck in this infinite loop if everything goes correctly, because once we have stored these values, nothing is changing them, right? Nothing in this program changes them. So let's see if this works. Okay, so our program counter is 0. We load the value 1 to register 1. Program counter is 2. We load the value 1 to register 2. Now look, our jump flag is set, and we are subtracting 1 from 1, and we're getting 0, and our 0 flag is set. When we AND these together, it tells our increment or jump to jump. And when we get a falling edge, aha, our program counter jumped back to 1. Now it'll increment back to 2, but then instruction 2 again tells it to do the jump, and so we wind up on the falling edge, returning back to instruction 1. And we can do this forever. The GIF just reset. So we did not actually go back to instruction 0 there. The GIF just resets at that point. So we now have an infinite loop, right? We load the value 1, we load the value 1, and then we compare these two registers, we see that they're equal, and we did that through subtraction, but just simply having the jump flag set, and that caused us to jump back to instruction 1, and then once at instruction 1, we incremented to instruction 2, which then caused us to jump back to instruction 1. And this is an infinite loop. Putting it all together, we now have a programmable CPU. We've built this CPU using the building blocks that we developed in the class, and extending them a bit, right? So we built all the way up to the register. We built the ALU, the 2-bit ALU, but we didn't build the program counter. We didn't build the instruction memory, and we didn't build the program counter, the instruction memory, and the register file, right? So those are the things that we did not build. But all of the components, right, we did develop. And we wired them together, and we made some decisions on how to represent instructions, and then we hooked the components together, programmed it, and ran that program, which allowed us to load two numbers and subtract. And then we edited the program, and that allowed us to load two numbers and then jump if they are equal. So this is a very simple computer that is fully implemented in the NAND game. And I hope it helps you understand how all the things that we've seen so far come together. Now, the story of the CPU is going to keep going. We're not done with the CPU, because while this is everything that we are going to talk about at the basic level, this CPU has some serious limitations, not just the one that we developed in the NAND game, but the RISC-V single-cycle CPU that we have described so far has some serious limitations. And if we are going to actually have a CPU that is usable in the way that we have come to expect CPUs to be usable, then we're going to have to make some changes to it and improve it significantly. And that's where we're going to be going next. So I mentioned in class that if you are so inclined, you can build the CPU in the NAND game, and you can make a presentation, a short presentation, so I'm thinking probably 5 minutes, over your design decisions, how you put it together, and demonstrating that it works, and you can get extra credit. So that's just something that is available if you are so inclined. Wanted to mention again here at the close. I hope this has been helpful in understanding how it all fits together.